Hello and welcome to Cisco Router Training 101. My name is Don Crawley. I'm from soundtraining.net. We're the Seattle, Washington-based publisher of learning resources and provider of accelerated training for IT professionals. This time we're doing Understanding an IP Address. It's based on Chapter 3 in my book, The Accidental Administrator, Cisco Router Step-by-Step Configuration Guide. The book is not required for use with the video, but if you'd like to follow along, it is available in both paperback and Kindle editions from Amazon and through other resellers online. What is an IP address? Well, here you see the TCP/IP settings, network connection details from a computer running the Windows 7 operating system. Now you'll notice this says IPv4 settings. There's two types of IP addresses, IPv4 and IPv6. We're going to focus in this video on IPv4, which is often just known as an IP address. IPv6 will be covered in a separate video. So here you see the IPv4 address, 192.168.1.7. And then you also see the IPv4 subnet mask of 255.255.255.0. Now, as I said, that's from a computer running the Windows 7 operating system. Let's take a look at the output of the command show interface G0/0 on a Cisco router. And this is just showing us the parameters set for this particular interface, but it's really kind of the same thing as we saw on the Windows 7 computer. Here we see the internet address. This is the IPv4 address of 192.168.101.1, but then there's this strange /24 at the very end, and that is simply another way of indicating the subnet mask, and it means exactly the same thing as what we saw on the previous slide, where we had a subnet mask of 255.255.255.0. We'll get into the significance of that and what those different types of notation mean as the video progresses, but for right now, just know that /24 is another way of expressing the subnet mask of 255.255.255.0. When we talk about IP addresses, we have to talk about two different types of addresses. There's the host or node address, and then there's a network address. We're going to use the term host and node synonymously. They don't mean exactly the same thing, but very, very close. So we'll use them synonymously for the purpose of the video. And a host or a node is a single entity on a network running the Internet Protocol, or IP, in this case IPv4. And a network address represents a whole group of hosts, such as what you see in the graphic. A good way to think about it is to compare it to telephone numbering, where the phone number, 206-555-1212, in this case, represents a single entity on a telephone network, and the area code 206 represents a whole bunch of local phone numbers, multiple entities on the network. Now let's go to an example. Here we see an IPv4 address. This is just some random address that I chose, 208.79.115.3. Each one of those sections is called an octet or a byte. And the reason they're called octets or bytes is because they map to 8-bit binary numbers, and there's 8 bits in a byte. Now a bit is simply a contraction of the term binary digit. And every IP address, IPv4 address anyway, is made up of a total of 32 bits. Divided into 4 sections, again called octets or bytes. Bits exist in one of two states. They're either on, in which case they're represented by a 1, or off, in which case they're represented by a 0. Let's take a look at an example. So we'll just pull one group of bits out of this address, and it could be all 1s, like what you see here. It could be all 0s, or it could be a combination of 1s and 0s, such as what you see here. Now how does it work? Well, every bit has a corresponding decimal value, ranging from 1 to 2 to 4 to 8 to 16 to 32 to 64 to 128. And to determine the decimal value of the byte, we simply add up the decimal values of each of the bits that are turned on. So let's take a look at an example. Here the 2-bit and the 1-bit are turned on. We simply add 2 plus 1, and we get a byte value of 3. So the decimal value of this entire byte is 3 because the 1-bit and the 2-bit are the only bits that are turned on. Here's another example. In this case, the 4-bit and the 2-bit are turned on. We add those together, 4 plus 2 equals 6, so the decimal value of the byte is 6. And one final example. In this case, the 32-bit and the 2-bit are turned on. 32 plus 2 equals 34, and that is the decimal value of this byte. Now, in the real world, you may see 5 or 6 bits turned on, but same thing. You just add up the decimal values of the bits that are turned on to get the decimal value of the byte. Now, let's dissect that address a little more. As I mentioned, each one of the bytes represents an 8-bit binary number. So 208 maps to 11010000. 79 maps to 01001111. 115 maps to 01110011. And 3 maps to 00000011. Well, let's see if we can figure out exactly how we arrive at these numbers. So let's start with the leftmost byte, the 208. Now 208, as we said, maps to this binary number, but let's take a look at it a little more closely. Here you can see the 128-bit is turned on, the 64-bit is turned on, and the 16-bit is turned on. So we simply add 16 to 64, which gives us a value of 80, and then we add that to 128. Well, 128 plus 80 equals 208, and that's where the byte value of 208 comes from. It's really pretty simple, as you can see. Let's take a look at 79. 01001111. Well, let's take a look at where that comes from. In this case, the 1-bit, the 2-bit, the 4-bit, the 8-bit are turned on, as is the 64-bit. So 1 plus 2 equals 3, plus 4 equals 7, plus 8 equals 15, plus 64 equals 79. Now let's take a look at 115. And in this case, the 64-bit is turned on, the 32-bit is turned on, the 16-bit is turned on, the 2-bit is turned on, and the 1-bit is turned on. 1 plus 2 equals 3, plus 16 equals 19, plus 32 equals 51, plus 64 equals 115. And yes, by the way, we usually do add them up from the right to the left. Now let's do the last one. This is pretty simple. I'll bet you could do this one in your head. In this case, the 1-bit and the 2-bit are turned on, therefore the byte value is a total of 3. Before we go any farther, I think it's important to mention that in the early days of the Internet, the address space was divided into 5 classes, 3 of which were used in commonly applied IP addresses, Class A, B, and C. Now, the significance of this is that Class A addresses were assigned to networks with a large number of nodes. In this case, you can see a little over 16.5 million nodes per network were supported. We use the number 1 through 126 to identify it as a Class A in that first octet, and then we use the last 3 octets for the host portion of the address. So the first octet was used for the network portion and the last 3 for the host. Next, we'll take a look at a Class B, which was used for medium-sized networks. In this case, it supports 65,500 hosts, approximately. Well, we use the first 2 octets for the network portion, the last 2 for the host. That first octet has to fall within the range of 128 to 191. That identifies it as a Class B. And then for a Class C, the first octet has to fall within the range of 192 to 223 inclusive, and we use the first 3 octets for the network portion and the last 1 octet, the 4th octet, for the host portion. Now, you may wonder where these strange numbers come from. And there's a very important formula that I want to introduce you to. It's one that you're going to go back to time and time again, and it is 2 to the power of n minus 2. 2 because we're dealing with a base 2 number system, to the power of n, where n equals the total number of bits we're working with, and minus 2 because of internet rules that we'll talk about in a different video. So if you think about the Class A network, you'll notice that there are 3 octets that make up the host portion of the address. How many bits are in each of those octets? If you said 8, you got that correct. So that gives us a total of how many bits to work with for the host portion of a Class A address. The answer is 24. If we take 2 to the power of 24, it gives us 16,777,216. We subtract 2, and that's where that number comes from. So anytime you want to know the total number of hosts available on a network, you take a look at the total number of host bits, take 2 to the power of whatever that number is, in this case 24, subtract 2, and that tells you how many hosts or nodes you can have per network. So what do you suppose the formula is for a Class B? If you said 2 to the power of 16, you'd be right. Well, 2 to the power of 16 minus 2 gives us 65,534. And for a Class C, it's 2 to the power of what? Well, if you said 8, you'd get it right, and it would give us 2 to the power of 8 minus 2, or 254 nodes per network. Now, as I said, this formula of 2 to the power of n minus 2 is an important one that we're going to come back to time and time again as we work on IP addresses. For now, just know that, maybe write it down in red so that you'll be able to come back to it easily in the future. Now you may also wonder where those first octet values come from, and it's from the leading bit pattern, and we're not going to go into a lot of detail on this, but I did want to include this graphic so that you could see where it comes from. A class A address always has a leading bit of 0, so the leftmost bit is always 0. Therefore, the first octet has to fall within the range of 0 to 127 inclusive. Because of Internet rules, we limit it to 1 to 126. A class B, the first 2 bits are always 10, which mathematically would give us a first octet value of 128 through 191 inclusive, couldn't be anything else. And for a class C, the first 3 bits are always 110, which gives us a first octet value of 192 to 223 inclusive. Again, can't be anything else. Now, earlier we did the binary conversion where we went from binary to decimal. Now let's go from decimal to binary. And the way we're going to do this is with a table, which you see on screen right now. And the rows in the table represent the octets of the IP address that we're going to convert, and the columns represent the decimal values of each of the bits in an 8-bit binary number. So the first thing we do is we ask ourselves, can we subtract 128 from 200? The answer is yes, so we put a 1 in the 128's column. That leaves us with a remainder of 72. Can we subtract 64 from 72? Yes, so we put a 1 in the 64's column. That leaves us with a remainder of 8. Can we subtract 32 from 8? The answer is no, so we put a 0 there. What do you suppose goes in the 16's column? Well, if you said a 0, you'd be right. We're still dealing with that remainder of 8. Can we subtract 8 from 8? Sure, so we put a 1 in the 8's column, and that leaves us with a remainder of 0, so we put a 0 in each of the 3 remaining columns. Now let's do 191, and I'll show you a really cool trick. Can we subtract 128 from 191? Sure. So we put a 1 in the 128's column, leaving us with a remainder of 63. Can we subtract 64 from 63? No. So we put a 0 there. But look what we put in the remaining placeholders. All 1s. And the reason is simple. This is the trick. Because anytime you have consecutive 1s from least bit to greatest bit, the value is always going to be 1 less than the next highest bit. For example, 1 plus 2 equals 3, 1 less than 4, 1 plus 2 plus 4 equals 7, 1 less than 8, and so on. Therefore, 1 plus 2 plus 4 plus 8 plus 16 plus 32 has to equal 63. It's very cool. Try this the next time you're at a cocktail party. Show them. They'll be impressed. Let's try 127 now. Can we subtract 128 from 127? Nope. So we put a 0 there and 1s in the remaining placeholders. Now before we go on, let me ask a question. Suppose instead of an 8-bit binary number in which the highest order bit is 128, what if we had a 9-bit binary number? What would the highest order bit value be there? Well, it would be double 128, or 256. Therefore, if you have an 8-bit binary number in which all of the bits are turned on, what is its value? Well, remember, it's going to be 1 less than the next highest bit, or in this case, 255. Now, is that a number we see frequently? Sure, you see it a lot, especially in a subnet mask, right? So just remember that anytime you see an 8-bit binary number in which all of the bits are turned on, it has a value of 255. And conversely, anytime you see a value of 255, that represents 8 bits all turned on in binary. Now let's do 65. Can we subtract 128 from 65? Nope, so we put a 0 there. What goes in the 64's column? Well, it's a 1, and we put a 0 in each of the remaining placeholders until we get to the very last one where we put in a 1. So the binary equivalent of 200.191.127.65 is what you see at the bottom of the screen. And about now you should be asking yourself one of 3 questions, maybe all 3. So what? Who cares? What's in it for me? Well, let's see if we can answer that. With every IP address, there's always a what? A subnet mask, right? And what's the point of the subnet mask? What does it do? Well, let me see if I can explain it. What class is that address? 200.191.127.65. That is a class C address. We know that because of the value of the leading octet, the leftmost octet, which falls within the range of 192 to 223 inclusive. That makes it a class C. How many bits make up the network portion of a class C address by default? Remember that table that we had earlier? And it's always 24 bits that make up the network portion of a class C address by default. How many bits are turned on in the subnet mask? Well, let's see, 255 always equals 8 bits turned on, right? So 255, 255.255. Let's see, that's 3 octets, each of 8 bits. 3 times 8 is 24. There's 24 bits turned on in the mask. Do we see a correlation here? If the bits are turned on in the mask, the corresponding bits in the IP address are network bits. In this case, bits 1 through 24 are turned on in the mask. Therefore, bits 1 through 24 in the IP address are network bits. This is important for you to remember. In order for 2 nodes to communicate on an IP network, the network bits of their IP address must match, or a router must be placed between them. Now, let's take a look at an example that may kind of throw a wrench in the works, but it's the same concept. Look what happened here. The network architect stole 2 bits from the host portion of the address. Now we have a subnet mask of 255.255.255.192. What does that mean? Well, that simply means that we've extended the mask by 2 bits into the host portion of the address. If you think about it, the only 2 bits that could be turned on to equal 192 are the 128 and the 64-bit. So those are the only 2 that could result in that number. Therefore, those 2 are turned on. And now what we have is we still have a major network number of 200.191.127, but look at the value of the bits turned on between the 2 lines in the IP address. It's the second of the first 2 bits. The 128-bit is not turned on, but the 64-bit is. Therefore, the value of the bits between the 2 lines is 64, and that is our new entity called a subnet ID. Now, the subnet ID you can really think of as just a subnetwork. In fact, that's where the term subnet comes from. It comes from the subnetwork of the larger network. Now, our host ID in this case is 1. We add 1 to 64 to get the 4th octet value of 65. But what's not so clear to the eye is where the dividing line is between network and host. And in this case, it's between bits 26 and 27. You'll run into this from time to time, and what you need to understand is that in order to know where the dividing line is, you have to understand how the subnet mask works. Now, in the real world, you'll probably use a subnet calculator, but if you're thinking about taking a test like Network Plus or the Cisco CCNA, you can't take a subnet calculator into the room with you, so you'll have to understand how this works. So what's very important for you to understand is that the subnet mask identifies which bits in the IP address are network bits and which bits are host bits. And whether it's expressed in traditional dotted decimal notation like 255.255.255.0 or in the modern what's called CIDR or classless interdomain routing notation, /24, it means exactly the same thing. It means that the first 24 bits are turned on, the first 24 bits are network bits. And you may see a /18, but all that means is that the first 18 bits are turned on, and that the last 14 would be host bits. So the first 18 would be network, the last 14 would be host. But again, the most important thing to remember is that subnet masks identify which bits in the IP address are network bits and which bits are host bits. In subsequent videos, we'll talk about how you can use that understanding in routing and in access control lists and in almost every other aspect of a router operation. If you'd like to learn more, we have other resources available for you at our website at www.soundtraining.net. I blog at soundtraining.net/blog. You can follow us on Facebook, Twitter, and Google+. And if you'd like more videos, there's more videos for you at our video channel at www.soundtraining.net/videos. And you can pick up the companion book at our bookstore at soundtraining.net/bookstore. Well, I hope it's been helpful for you. For soundtraining.net, I'm Don Crawley. Thanks for watching. We'll see you next time.